Okay, so one announcement, and I don't have the date with me right now, but coming a couple of weeks out is ASHRAE Student Night in Nashville. It is a mini job fair, and we have lots of TTU. I bet 20, 30, 40% of the people that come from the companies are TTU grads. It's like old home week. And dadgummit, this is the third one in a row. I'm going to have to miss this one too. Languri is going to take a van. It's a Thursday. It's a couple of Thursdays out. I'll get emails out and all that. But you really should think about going. They don't have a sit down dinner, but they have finger foods, and it's a great opportunity to get out and talk to people. Anything related to HVAC. Train is often there recruiting, the Train office for consulting type engineers, also the manufacturing facility up in Clarksville. They recruit out of there. Test and Balance, United Test and Balancing, big test and balancing firm. All the design firms recruit there. And Tennessee Tech is usually the lead institution for, I mean, we just dominate Central Tennessee as far as the HVAC, consulting, construction, putting mechanical engineers out there. So we've had multiple people get job offers, so I would plan to attend if you can. I think Languri plans to leave at 3:45, and you'll get back about between 9 and 9:30. They'll feed you finger foods, and you get to meet students from TSU, Vanderbilt, Lipscomb. I guess that's primary. There may be a few other schools contribute, but Tennessee Tech usually dominates this thing, and we kind of have a tradition. So I'm gonna whoop it up, let y'all know. But really, it's a very good opportunity to go talk to some people. I mean, it's laid back enough and it's long enough that, it's like you go to the career fair over here and there's so many people and so many booths and all that. Sometimes it's hard to get some time with people, but you got plenty of time to get around and talk to all of the people, find out what they do, what they're looking for. And, if they're not looking for somebody, those guys will try to refer you to somebody else. But I hate it that I've got another trip lined up, because it's kind of like old home week, but it's a lot of fun. So anyway, Languri will take a 15-passenger van. Beyond that, sometimes people want to drive, this day and time. But it's at Lipscomb University in the student center there, and they do a real good job. It used to move around, but Lipscomb has done such a good job, and they're willing to have it every year. That's kind of found a home there, and it works out real well. So hopefully you can plan to attend that. Okay, let's see. So let me talk about the homework a little bit. So the idea is, and I have a little PowerPoint file that shows you in very crude terms what this building looks like. It's like 600 feet by 370 feet, and it's got 1, 2, 3, 4 zones, north, south, east, west, and a central core area. And that's what's in that file. So, but since we're in this course, we're going on and looking at, chillers and cooling towers and interaction and energy and all that sort of thing. So you kind of start with that. And then you're asked to run these simulations. So simulate the following: airside economizer. Well, you probably don't know what that is, but this Train Engineers newsletter talks about it, and I'm going to talk about it a little bit today. Basically, it's free cooling with outside air on the air handling units. When it gets cool outside, why do you want to run mechanical refrigeration? It's like opening the windows. It's just that the HVAC system does it for you. Setback. That's just an automatic thermostat, programmable thermostat, where you can say, okay, the building's occupied at 7 o'clock in the morning. I'm going to leave and everybody leaves by 6 or 7 o'clock at night. So I'm going to change the thermostat settings automatically so I can save some energy. So that's what setback's about. Run base case with cooling tower fan. And then an option on cooling towers is to use a variable frequency drive instead of just having an on-off switch with a constant volume fan. That's an option. You just turn on a switch, and I mean, once you figure out what you do, how to operate this thing, these are not very difficult. And then we're going to put in a different chiller type. We've got a water-cooled centrifugal in it, and you're going to go to an air-cooled scroll type. So these are different types of water chillers that are on the market. So an air-cooled will not be as efficient as a water-cooled. But, so the chiller will be less efficient, but you do lose a cooling tower, because if it's air-cooled, you don't need a cooling tower. And then I tell you what I want you to tabulate, and I want you to put that in a little Excel sheet and kind of compare the electric rate that you use. This is GSA 3 out of Nashville. I want you to program that in. We'll go over that briefly, how you put in the electric rate files. And then we got cookful gas rates. We can use that. I think I said, say in there, I don't know, I give a, I forget what I say. I've been running like crazy lately. Let me see. It says which gas rate to use on the back of one of these pages someplace, doesn't it? We'll pick one. I don't really care. You can pick whichever one you want, to be honest with you. I thought I had it on there, but maybe I didn't. I don't know. Utility rates. Nah, anyway, I guess I didn't get it in there. Okay, so that's what that's all about. We'll get back to it later. I think I want to pick up and finish the presentation we were in last time. This is on the economics of absorption refrigeration, and we had just gotten down to this where we had kind of calculated the operating cost for this various types of chillers. So single stage absorber, it was what, 0.24 therm, and a therm's 100,000 BTUs per ton hour, 12,000 BTUs per hour of refrigeration. And our price was 45 cents a therm, or that's $4.50 a million BTUs. And so we went down through all of this. We got a two-stage absorber. We got a direct fired, which would be a two-stage absorber, direct fired, and a centrifugal chiller, 0.6 kW per ton. And so you see, right now, it looks like, well, why would, given these two rates, $4.50 a million for gas and 8 cents kilowatt hour, it looks like you wouldn't want to mess with this stuff. Well, so where the payback comes with sometimes doing this is this time of day metering, where you have on-peak periods during the day where the price of electricity is really, really high. And then you have off-peak periods where it's not nearly so high. Okay, and so we're going to investigate that a little bit. The other being, if you can, in an industrial facility or something, you can come up with free heat, then this cost goes basically to zero once you put in some heat recovery equipment. Then it has a really compelling payback. Okay, so the goal in this presentation, this is put together, this is a little bit of marketing stuff by Train, I guess, but it kind of shows one way that you can make this stuff pay off. Design an application that uses the direct fired absorber to reduce as much demand as economically possible. And so that demand charge in your electric bill, you get billed on the amount of energy, electrical energy, kWh, that you use, but you also get billed on that peak, kW. And if you're running a big chiller like that, say that centrifugal is 0.6 kW per ton, 1,000 tons is 600 kW, you could be paying $20, $25 a kW per month if you run that during the on-peak period. So the idea, hey, let's have an alternative. The other thing I'm saying is that you can address this with is ice storage. You can have some chillers that you can run a glycol solution and produce really, really cold water, 20-degree glycol laden water so it doesn't freeze. Run that through an ice generating tank say you do that at night when the demand cost is really low, and then you simply generate your chill water by melting the ice during the daytime. There's Erlanger down in Chattanooga I believe they have an ice storage system. So, you know, the economics of these things bounce around, you know, it sounds like prices right. You know, somebody figures out how to do something cheaper, and all of a sudden ice storage gets cheaper, and that might make it economically better than an absorption chiller. Well, then there may be some sort of a breakthrough on making absorption chillers, and all of a sudden they get cheaper. And so this stuff, it moves around. It doesn't do it super quick, but from one a couple year period to the next couple year period, the preferred project economically may change to do the same job. So anyway, so that's what this is about. Okay, so economic analysis, these are all of the items that have to be considered. You got to figure your load profile, first equipment cost, what's going to cost to put it in, operating, maintenance, total system, all that kind of thing. There's lots of engineers out there in the real world. This is how they make their money. I mean, Trane isn't going to pay you to come and do, simple little building designs. Now, Smith, Seckman, Reed, they might hire you to design the new NHL arena that's being built in Los Angeles, because that's what those people do. They do renovations on, NFL football stadiums, and the HVAC, and the guys that sit outside, they don't have HVAC, but the guys, do you think Jerry Jones is sitting in Dallas? You think he's sitting out there in the sun? And of course, it's almost closed. But Jerry, when they show Jerry on TV, he's up there behind the glass, man. He's got the bar over here and the buffet behind him and all that sort of thing. Jerry is going to be comfortable because Jerry writes the checks, right? Have y'all ever been to a UT game and set up in the boxes? I got up there one time. We got some friends that own Bank of Putnam County. And Bank of Putnam County is a $1 billion company. Can you believe that? Little Bank of Putnam County, they're growing like a weed. That might be a good investment. I don't think it's publicly traded. I think they hold it all. My son went through, best friend is in line to inherit the Bank of Putnam County, so we treat him real nice. But anyway, we got invited one time to go. They had a luxury box that they would take all their, and they didn't have it booked. So they rented a bus and hauled a bunch of us down there. And, we had the beer keg and the wine on the bus, and they pull you right up in front of the door, and you walk in, you get on the elevator, you go up, go down in your box and sit there. Of course, there's a TV monitor there because you're pretty far up, but the buffet, and it's not bad. One time I made it. Anyway. How do we get off on that? All right. This is looking at different way that multiple chiller plants get piped up. And so, this may be a little bit beyond what we're going to do in here, but nonetheless. So what you've got here, you're showing electric centrifugal and the direct fired absorber. And it turns out if you pipe it up like this is not the best way to pipe it up. You wind up loading these things 50% each, and that's not just the best. But it's possible. You can make that work. This is series. Operationally, this is much more flexible, that you put all of the chill water through the absorber, and then you put it through the electric centrifugal chiller. There's some characteristics down here. The big downside of this is you've got the pressure drop going through this one, and you've got the pressure drop going through this one. So you kind of always paying a double pressure drop. It's one of the advantages of this is that these absorbers have more capacity if you give it warmer water. And so this might be a 1,000-ton chiller, but if I can get 58-degree water, that 1,000 tons would be based on like 54. if I can put 58-degree water in this, I can probably get 11 or 1,200 tons of cooling out of it because I'm not pulling it down. And then so you take a big chunk of the cooling here, and then you finish it off with the centrifugal. So that's a possibility. And then there's this Sidestream arrangement. This is pretty recommended too, because it has that same advantage. You've got your direct fired absorber here, and so this is the warm water coming back. You can pull as much as you want or all of it through this guy, maximize its production. And then if you can get it cold enough, then you can shut this off and you can just use the bypass. I think, well, the bypass could run either way, but you can go this way back out to the system, or you can come up and then you could put some water through here. You could bypass some, you could spread it out between this. So you get a lot of operational flexibility out of this sort of an arrangement. Okay, so now on to the analysis. So basically what we're going to claim in this analysis is that we're going to avoid the demand charge with the absorber, because it can cool all day long, but it doesn't hardly have any electrical demand. And so, you know, the electrical demand is going down, and we're gonna buy that natural gas to make our chill water during the on-peak periods. Off-peak, we go ahead and run the centrifugal. So, and it's interesting, I guess in DC, I don't know that I've seen time of day rates that have 3 different blocks during the day, but apparently they do. The energy charge, and I don't know the exact hours. I think we can we get a little bit of that later, but on peak, this is the energy. This is not demand, but the energy is about 5.32 cents a kilowatt hour on peak, mid peak 0.04, and off peak about $0.027 per kilowatt hour. And there's 2 different pieces of the demand charge, but you're going to pick up because this, if you're running the centrifugal, it's going to peak during the maximum demand will occur during the peak period. So basically you get to add these 2 together. And so that's $22 and almost $23 a kW. That's a pretty steep demand charge. Okay. This is kind of background information. Where are electrical costs coming from? So cost of operating a typical office building is, you know, kind of split. They're showing this, they're saying it splits about 50-50 between the demand charge and the energy charge, but the cost of operating a chill water plant is highly dominated by demand charges. So if you just segregate out the chiller plant, then you see 61% of the cost is tied up in demand and 39% is energy, because these things tend to have a high demand. Set that high peak. Okay, so here's how we can calculate the direct fired operating cost. Okay, so we need to think about this. So remember the definition, COP, right? What's COP stand for? Coefficient of performance. What is COP? It's useful energy delivered divided by costly energy in. So it's like efficiency. Okay? So COP by itself is useful divided by costly. If I divide, that becomes costly divided by useful, right? And I've got 1 over that. So you can think about this 1 over COP as costly energy divided by useful energy. Well, the useful energy, if we're doing this per ton hour, is 12,000 BTUs per hour. That's by definition a ton hour. So I've got costly over useful. This is useful. So useful cancels out. I get costly, and that's going to be in terms of BTUs. Then I divide by 100,000, and that turns it into therms. because a therm is 100,000 BTUs. And then I multiply it by the cost per therm, and that's the cost to get a ton-hour of refrigeration. So I don't know. It's good to think your way through that. Make sure that you really understand what the calculation is. So this was the therms per ton hour for the direct from our previous analysis. So it's 0.1165. Therms of gas are, what is that? 100 thing. Well, what I don't do math in my head very good anymore. Anyway, that's the therms per ton hour times $0.45 or cents per $0.45 per therm. So it's $0.0524 per ton hour. Okay. So now we're going to look at the operating cost on the centrifugal, which we're comparing it to. And this is 0.6 kW per ton. That's what it takes to run the chiller. And then this is the demand charge, $22.80 per kW. So that's $13.60 per ton. And then this is the number of hours in the cooling season. They want to spread this out over the cooling season. So this is the number of hours in the cooling season over which we would be using energy at this rate while it was on peak and expensive. So a little bit of hand waving there. But anyway, so the levelized cost of demand comes out about 7.39 cents per ton hour. The energy charge is straightforward. It's 0.6 kW per ton. And so it's $0.0532 per kWh, so that's 0.03. So you add those two together and you get about $0.1058 per ton hour, including demand smeared out over the operating period where we could affect the savings and the energy. Okay, so now all of a sudden we're comparing 0.0524 to 0.1058, we got some savings, about 50% for doing this. Okay, so now here's a combination. They've gone through all of the peak periods. And so you're showing off peak, say you would not want to run the absorber because look, the centrifugal is like 1.64 cents. This is 5.24. You'd be shooting yourself in the foot to do that. Mid-peak, still shooting yourself in the foot, but on peak in the summer, and you got on peak in the winter. What happens in the winter, they have that same rate structure, but the electricity is not as expensive. They make it, it's in the summer where everybody's pounding the grid that they really jack the rates on peak. They jack them a little bit in the winter, and it depends where you are too. You know, so, you know, a different location, you know, like this winter might turn out differently. You know, you got to go through the analysis. But anyway, so you see, we've got a pretty good deal going on here. It's just a question, will that amount of savings be enough to justify the investment in the equipment? Okay, so let's look at some details on our example. Building Washington, D.C. with 1,000 tons of load, cooled by 2 machines. One 400-ton direct-fired absorber, COP 1.01, and a 600-ton electric centrifugal at 0.6 kW per ton. Design conditions, 42-degree leaving chill water temperature. That's a pretty standard number. You know, someplace between 42 and 45 is what you're going to need to see, especially in a humid climate. What happens is if this creeps up too much, the water's not cold enough in the coils and the air handler to condense out the moisture in the space, and you lose humidity control. So in a drier climate, you can provide pretty good sensible cooling with warmer temperatures. But Tennessee, eastern part of the US, you're going to have in the summertime when there's humidity load, you're going to have 42 to 45 degrees. Tech, I think, runs 42. And by the time it gets to the building, you know, it's piped underground and pumped and all that stuff and comes up in Brown Hall. We're probably 44, 45. When it gets to the end of the line, it may be even, you know, 45, 46, something like that. So you got to be a little careful about that. You know, you can lose that, but you lose that moisture, that dehumidification capability before you lose a major part of the sensible cooling. There's our cost and DC electrical rate structure. So there's the building profile. So we're seeing the electrical is providing this portion, and the direct fired absorption is the brighter blue. And so this kind of shows you this is when this on-peak period must be, because that's when they're operating it from 8 a.m. to 8 p.m. So they've got a 12-hour, you know, on-peak window. And so you see, this is, as this comes up, and I'm, you know, the breakdown between the loads, I'm not sure. Well, this may be the on-peak here, because this is where they're maxing out the absorber. I'm not real sure. They don't give a very good explanation in here, because say we're splitting the load. 400 tons is the absorber. See, it can come up to that, and they're only bringing it up 1, 2, 3, 4, 5, and then the load was a little bit less. So basically 6 hours. This may be that on-peak period, and they're ramping the thing up to get it ready to go. But you can see during the peak portions of the day, 12, 1, 2, 3, 4, you're, you know, you're not quite at 1,000, but you've got 400 here, and you're loading the centrifugal pretty good. But what this does is that if you didn't have this absorber, you would have another 400-ton electric chiller, so that you were able to condition the building. So you can kind of see the bite out of the total load that they're showing the absorption chiller taking. Results. Direct fired system saves approximately $27,000 per year in operating cost. Lower cooling tower flows can decrease the installed cost while improving system efficiency. Maintenance costs for the new direct fire, you know, it's possible for that to rise later, certainly. So anyway, and they don't give a payback, so, you know. But anyway, it gives you some kind of an idea of one type of scenario that you can look at the absorption for. Lots of developments in the last, I don't know, 5 to 10 years that have made this technology more robust. You can just look at a history of some of them. I mean, these things have been around a long time. Just they continue to make the microprocessor controls and all have really made some improvements. Typical problems, we talked about some of this before. If I can take that bar. I don't want to do that.
Roughly, how much does an absorption chiller setup cost?
You know, I'd have to dig. I don't have, they cost more than, I would say they're probably 10 to 20% more. I don't have a good number off the top of my head. I've got some stuff buried on the computer, but it just doesn't come up to me right now. Sorry. I'll try to get something back to you on that. But crystallization, we talked about that. We have the high salt concentration, low temperature. This stuff can crystallize. And for these reasons, we went over some of that. Slow response time, that's been a wrap on them. And difficult to operate and maintain. Air, because, you know, the vacuum is pretty hard. Corrosion, and there may be, there may be a shortage of service personnel. I don't know. Solutions, controls, material feature, robust design. Variable frequency drives. Oh yeah, so you do have those two electric videos out there to watch, and you will have a quiz a la this on a week from today on those, because I want you, they're pretty good, and you need to know the basics on an induction motor and also on a variable frequency drive, how those things operate. So they're pretty good videos. Controls, we use in VFDs on everything these days. You won't buy a pump or a fan today hardly without a VFD for speed control. It's just where everything is gone. Part load operation, turn down capabilities are similar. That's gotten better. Lower maintenance on burners, and shutdown is better. So they've gotten better. Lower chill water temperatures, it can now go down to 40, which was not possible before. And remember, on this direct fired unit, they can make hot water for space heating as well as chill water for space cooling. Now you got to pick one that you're going to design for. If you pick the cooling, then you just get a certain amount of hot water. If you pick the hot water, then you get a certain amount of cooling, then you got to kind of make sure that fits your applications. And changeover can be done remotely, computer-based. So in the materials, the generator sees the highest temperatures and concentrations. So stainless steel, that's one reason it's expensive. Stainless steel is not cheap. And then tube materials have been improved. Low NOx burners on the direct fired to reduce NOx emissions. Modularity, automatic purge to get the air out of the system. This shows some reactions. Oh my goodness. I didn't make it through to review this. Let me see. Let's look at how, this is how the automatic purge. Okay, at the 40-minute mark, they put a bunch of nitrogen into the system. Okay, I couldn't remember. Okay, so at the 40-minute mark, this is minutes. So they introduce nitrogen into the system, and you can see the reaction. That's like if you had a leak, and you can see burner firing rate goes down, capacity goes down, but basically they're showing the evaporator temperature. You know, I mean, it did a pretty good job. What they're showing here is that the controls, addition of 6,000 milliliters of nitrogen to the absorber at 27 to 47 minutes. So back in here, and then you look and see what the data on the machine looked like. So it handled it pretty well. I got to do this. Okay, so this is where the colder condenser water temperature was an issue as well, as far as crystallization. And so they dropped the cooling water temperature pretty radically from what's at 105 down here to about 55 over the course of, what is it, 10, 20, 30 minutes, something like that. And you see, initially the machine said, holy cow, what's going on here? So it took some pretty drastic action. But, I mean, this is only a 20-minute transient, and it levels it out pretty well. So this is just a demonstration that the controls have gotten much better. In the old days, this would have probably caused a shutdown. Oh, and this is cycling the cooling tower water. And they're doing their best to screw this guy up from about 95 down to about 65. And you see the pattern entering cooling tower temperature. Yeah, cooling tower variation. So you see how the evaporator responds. This is entering water temperature of the evaporator. This is leaving water temperature from the evaporator. I mean, that's pretty darn good. This is the yellow line is the set point. So, when you're monkeying with it to that extent, I'd say they were probably pretty happy with that result. What are we doing on this one? Evaporator flow rate, I don't remember. Anyway, I'm not gonna. Okay. System issues, hybrid plants. A hybrid plant would be a combination of a centrifugal along with a absorber. Lower tower GPM. These are some things people are trying to do to save energy. I know in conventional plants, they're going to lower flow rates to save pumping energy. Okay, that's enough of that. All right, so next place I want to go is, see if we can, let's talk about this economizer cycle a little bit here. So this is this handout. You should read through this. It's pretty common sense. I mean, it starts out here, like your grandmother in her kitchen baking a pie, and it gets warm. So what she does, she throws the window open. Well, so this picture kind of shows what the air handling unit is capable of. And let me make that bigger for you. And we'll talk through this for a little bit. Okay, that's pretty good. So, simple, like a single zone air handler. We just have one space temperature out here, sending information back to the controls. We got supply air being blown out by the fan. And that air temperature, what's a good supply air temperature? What kind of temperature are we looking for to blow in here in the summertime to keep this space comfortable? Any idea? What's that?
56.
Yeah, that's pretty darn good. Avery works in this stuff, so he got a leg up on. You better watch this guy. He's a ringer over here. Yeah, I would say 54 to 58. I mean, you're going to get a variation in this sort of thing, but certainly under 60. You getting your supply air up to 60. If you got any sort of a load, that's pretty questionable. But 56, if you got to pick a number, that's a pretty good number. Okay, and we got pressure sensors. The pressure sensor is controlling the fan speed, but that's not really what our purpose here is in this discussion. So we blow supply air out in the space, and then we return air, because we don't want to go on 100% outside air, because that's expensive. In the summertime, this might be 95. Okay, this return air from the space might be 80, 78. Depends on if you got any insulation on your ducts coming back. Well, you'd like to take as much of this 80-degree air and the minimum of your 95-degree air, because that's going to load the heck out of your system, right? So the ventilation codes tell us, ASHRAE 62, by code, how much, and it's based on the occupancy and the size of the space and all that sort of thing. That's on, when you fire up that carrier program, that's on that very first page where you describe the space usage, or you can put in your own numbers for ventilation. But this is the fresh air, and it gets brought in the back of the air handler. It gets mixed, so we call this mixed air down in here with this return air, and it goes back to the system. Now, if we want to use the open the window analogy, if it's, let's say we want 56 degree, okay, what if it's 53 degrees outside? Well, does it make any sense to run a big chiller or something, a big piece of mechanical equipment, to energize this coil to cool the air down? Wouldn't it be better if we could just take all of the air from outside at 53? By the time we blow it through this fan, it's going to pick up a couple degrees, a degree or so, blow it out to the space. Oh man, perfect. And all I'm doing is basically running a fan, okay? But when I do that, this could be a big fan. This could be a big space. I've got to get the air back. I got to get the air out of there, or the door's going to stand open if I just keep blowing in all of this air into this space. It's like blowing up a balloon. Well, of course, the walls can't move, but the doors can stand open. And I don't know if you've ever walked into a big building and noticed daggum doors are standing open, cracked. They got two doors and they're standing cracked open an inch or two, and air's gushing out in your face. Well, they've got too much pressure in the building, and it's caused by bad controls, something like that. Well, that's what would happen if we didn't have this fan, and this would be called a relief fan. And so then it takes that return air and it just blows it outside. So we actually probably had, now on small systems, this one fan may be enough. And you can do things I call gravity dampers that are just above the drop ceiling. And you put a little pressure on the inside and it's enough to force them open, and the air just flows out of the building all around the exterior shell. That's a cheap way, of allowing to relieve the pressure in the building when you go on. This is called economizer cycle. This is called an airside economizer. Okay? Questions? All right, well, let's go on. And y'all really ought to read this, at least a lot of it. There's really good information. The codes in some parts of the country, the codes require that you specify an economizer cycle. And there's the U.S. climate zones. It's not for us, but out west where it's dry and all, and it gets cool at night a lot, they require it. But you can say this is the energy code. What does standard 90 require? Well, that's the energy efficiency code. And most jurisdictions require that you meet, at least as a minimum, the requirements of ASHRAE standard 90 for efficiency. Here we go. Here's and this document's a little bit old. I don't know if this has changed any since this thing was published, but basically you see the parts of the country where it's, warm and moist a lot, not so much. Up here, if it's greater than 11 tons, economizer required if system is greater than 5 tons. So you see out west for sure. I think it is too now around here. Say ASHRAE 90, they come out with a new version of these standards every 3 or 4 years. And so, like I said, this thing may be a little bit dated. But okay, so this is the cool part right here. This is for constant volume. They have a little bit different. There's constant volume and variable volume. So constant volume means it's just the fan, when the fan runs, it just blows the same amount of air. And just you keep turning over there, you'll find this. So what we got here, this is maximum heating load. This is really cold outside. And we got maximum cooling load. So this is 0, or in Celsius, that's minus what is 0 Fahrenheit, minus 32, minus 15, 16? See, is that right? I think so. Something like that, because it was 0 minus 32 divided by 1.8. So I think it's 32 divided by 1.8 negative, I think. Anyway, you can check that. Verify that on your own. So this is cold, 0 Fahrenheit. Let's say this is 100 Fahrenheit or 95, whatever the design temperature is outside. Okay, so this is the outside airflow, and this is the return airflow. And of course, the sum of those would be the supply air to the space. And so we see when it's really, really cold outside, we don't want any more of that stuff. It's just too cold, you know. And we're on heating, so there's no need, you know, you just have to take whatever the code requires for ventilation purposes. So now it starts getting warmer, but we still say with constant ventilation air. So we have constant return air because this is a constant volume system. We're blowing the same airflow into the space all the time, okay? And then we get to minimum cooling load, okay? Well, this is still pretty cold. You know, a big building, interior core, you know, heat starts building up, whatever. So we hit a minimum cooling load. And so what do? Well, we start increasing the amount of outside air, you know, so that we can cool with outside air, which decreases the return air. Because remember, this plus this is supply going out to the space. Well, so it gets warmer. And notice this black area indicates energy savings because we're not running a compressor or a chiller or anything. We're just doing this with the ventilation, okay? And so we get more and more load. So we get more and more ventilation air, outside air, economizer air, and we get less and less return air. Well, this continues, and all of a sudden we get down here to the point where 100% outside air up here, we have no return air. We're just making the load. We're still no mechanical cooling. Life is great, right? Right. Okay. Then what happens? Well, it got 2 degrees hotter. Oh man, we can't cool them anymore. But so what do? Well, we're going to stay on 100% ventilation air because, okay, so you see at some point we go back down to minimum. So how do you determine where this point is that all of a sudden you say, no, I don't want any more ventilation air than I have to have? What do you compare? Of what? Of what? It's a comparison, right? You're going to compare. So you got to compare something, you got to have 2 quantities. Return, because what are my options? I can put air, I can put return air through here, or I can put outside air through here, right? So what am I going to compare? Now, Avery's been around the block a time or two, and so he threw out the enthalpy word. Cheap, and in the old days, enthalpy sensors are pretty good now. You know how they used to make enthalpy sensors? I even had to say this, when I was your age, it was based on the curling up of a human hair. You know how on a humid day you walk outside and your hair frizzes? You know, and they were based on the reaction of a hair inside some sort of a sensor. And they were expensive, and you know what? They didn't really work very well. So in the old days, we used to just compare dry bulb temperature. But if you compare dry bulb temperature, what are you leaving out? You're leaving out moisture. Because you can have a day, it's maybe 65 degrees, 20% relative humidity, you want all that stuff you can get. You may have another day which pouring down rain outside at 65 degrees, it's 100% relative humidity, and you don't want that stuff. You don't want any part of it because it's got so much moisture in it. Well, so how do you bring that into the calculation, into the determination? You sense enthalpy, because enthalpy is total energy, energy in the latent or the moisture, and energy, the sensible energy in the water vapor and the dry air. So that's what we want to do. We want to compare the enthalpy here, because I can get that across my coil, or I want to compare this enthalpy to the enthalpy outside. And I want to select the one that's less. You know, less energy into the coil, less load on the coil. Everything's good. Okay? So that, what's that assignment sheet say? Integrated dry bulb, and integrated means a sensing continuous control system like this. So, but in the Carrier software, you can base it on dry bulb temperature, or you can base it on enthalpy. And so I want you to run both of those and just see what kind of a difference it makes. So that's what we're talking about on the economizer. Now let's finish down here. This is a cool, I don't know who came up with this diagram, but this is a pretty good diagram. This pretty much shows it. So what's happening here is we've had to start mechanical cooling. This is mechanical cooling capacity because the outside air is just not cold enough to do it, right? But we're staying on 100% ventilation air because the enthalpy of this is less than the enthalpy of the return air. And finally, we get up to some point and that switches, and we go, oh crap, we don't want any more of that stuff than we got to have. It's too energetic. We'd rather have return air. And all of a sudden, this plummets down to here, and the return air then jumps back up to here, and we're in the same situation we were over here, except now it's hot outside instead of being really, really cold. And then, you know, as it gets hotter and hotter, the mechanical system has to do more and more cooling to keep us comfortable. Okay? Pretty cool. Now, we're running out of time. This is, I don't know if I can, sometimes I have to go review these things. This is a variable air volume system. Okay, so let me talk to you a little bit about that. So what this VAV system does, and this isn't a terribly good diagram for it, but a VAV system, this is a supply air duct. So I got my 56-degree air, and it's going down here. And I get down here to the first office, and I come out of that, and it goes into what's called a VAV box. And a VAV box is just a variable volume damper. And that variable, the amount of air that gets through that damper is controlled by the thermostat in the space. Okay, so if the space starts getting too cold, the thermostat says, hey, damper, close down. I'm freezing in here. And so the damper closes off a little bit. And so it's constantly giving feedback back and forth to adjust that damper position, which adjusts the airflow into the space. And at this level of conversation, we would assume the 56 stays the same. In a big, sophisticated system, there's actually some reset on that, but that's kind of like icing on the cake. Right now, you can just think about 56 as 56. And I may have 10 or 15 or 20 boxes coming off of that. And some may serve the east, the north, the south, the west, all around. And so when the sun's over here in the morning, the sun's over here on the east side of the building, all those east dampers go, oh crap, the sun's coming in the window, I gotta open up, blowing like crazy. Over on the west side of the building, the sun's not over there, those boxes are saying, hey, what do you do? I don't have hardly any load, so they close back down. Well, as these things move around, you take more or less air out of this main duct, that changes the pressure in the duct. And this pressure sensor is feeding back to the controls that are controlling the VFD that controls the speed of the fan. And so the pressure sensor and the fan and the VFD maintain a constant static pressure setting in the duct, whatever the boxes need. The boxes may need, 1.5 or 2 inches of water static pressure. And so that sensor is set to maintain a little bit above that to make sure I've got enough pressure so that when the box changes position, I get the right change in airflow and everybody stays happy in the space. So that's kind of what's going on with the VFD system. So it's a similar picture, but the story changes a little bit. Now, let's see if I can remember the story. I don't know if I can or not, but let's take a look at it. So again, same basic setup, really cold, really hot. Mechanical cooling is off, up until here, same kind of a deal. So let's look at what's happening. So let's see, we're showing, well, this is the cold outside air. And so that is again set by the ventilation code. When it's cold, we don't want, and we're in heating mode, we don't want any more of that stuff than we have to have. Okay. And so we're showing return air and total supply air going down. Oh, because it's getting warmer outside. Okay, yeah. This is set because we need more. Yeah, we need more air because it's colder outside. I had you can get your thinking flipped here. So as it gets warmer outside, we can ramp this down. This stays the same for ventilation. And so we get a minimum supply air right at the point where we need to start some cooling in the space. Okay. And so then it's getting warmer outside. The ventilation air is going up to handle that. And so the return air is ramping down at some rate. And so this plus this equals the supply air. Okay, and so as it gets hotter and hotter, we're still not doing mechanical cooling. It's getting warmer. We need more ventilation air. It's going up. This is ramping down. And the total supply airflow is going up because we have more cooling load in the space. And then we get to the point we can't cool it with the ventilation air. So now we get the mechanical cooling starts, comes up here. We're still on all ventilation air. We hit the high limit shutoff again. Bingo, this comes down here. Then the return air jumps up and we continue on. So it's a pretty similar story, but the picture looks a little bit different. And they do, I'm sure, a much better job explaining it in the handout than I'm doing. But anyway, that gives you some kind of an idea. Questions on that? Yoo-hoo. All right, we are moving. Now let's see. Okay. So we're pretty much free. Well, here, I won't start cooling towers today. Here, let me, I've got something else I'll show you. If I can find it. Yeah, I'll have to dig it out of the folder. Just a second. Under the chiller. Yeah, this is kind of interesting. I haven't, I may have, I don't know, if I haven't emailed this to you, I will. This is a steam-driven chiller that is a centrifugal chiller, but it has a steam turbine on it. It's not the absorption cycle. It is the regular vapor compression cycle that you looked at in the video and all that sort of thing. Instead of an electric motor, it's driven by a steam turbine. We visited Vanderbilt, their mechanical complex, a year and a half or so, maybe 2 years ago. And I forget the gentleman's name. They was very gracious, and we took a group of students and went through all of that. And they had absorption chillers, they had centrifugal chillers, and they had a centrifugal chiller that's steam turbine driven. And that guy said, and he had experience operating, he said, I wouldn't have another absorber, but I would have as many of these steam turbine driven chillers as you can give me. So what those guys did is they were doing cogeneration. So they had a gas turbine feeding gas into a compressor and a turbine, all that. They take the hot exhaust gases from the gas turbine and they put it into a heat recovery steam generator, basically a boiler that makes steam from the hot gases out of the turbine. And they also had an additional, what they call a duct burner in there, where they could burn some more gas to heat those gases up more if they wanted to. That's making low to medium pressure steam, 150 pound steam. And then they're taking that out to the hospital for sterilization. They're, whatever heating needs they have at that time. Well, they were taking some of that steam through one of these guys. So I got a student that's working for Hobbs Company in Nashville, Andrew Holden. I guess that's too many years ago. Andrew's getting too old. He's like me. Y'all don't know him, but Andrew's doing great. Great young man through these courses and all. He's done super out there in the world. But anyway, so this is the spec sheet. We were looking at this with a couple other locations. And I said, well, just send me a spec sheet. I just want to see, what this thing looks like. And so you can look at some of the numbers. R134A, that's a typical refrigerant for a centrifugal chiller. This is 700 tons capacity. Entering water temperature, 56. Leaving water temperature, 44. Got a 12-degree delta T across the chiller. All pretty standard stuff. Refrigerant condenser, 85 in. I'm sorry, 85 into the chiller, 94 out. So that's our standard cooling tower, 95-degree water into the tower, 85-degree out. And then we also have a steam condenser, say, because this thing is putting steam into this turbine. What comes out of the turbine, it may be wet, but it's still a lot of steam. And so, you don't want to throw that away. So you're going to have to condense the steam out of the turbine that's driving the chiller. Okay, so we got 94 and 100 coming out. Rated flow, evaporator, 1396. Okay, so something to think about is GPM per ton. I don't even need my calculator for this. So we got 700 tons. What's the GPM per ton, roughly? 2 GPM per ton on the evaporator side. Okay. Let's see, flow rate. Condenser. I can do that math. Divide 2100 by 700. That's 3 GPM per ton. Okay. Now, when you do these absorbers, you're going to need more. Say, when you start simulating this thing, you have to be careful, these different chillers, that you have the right size cooling tower, because the condenser water flow rate changes. The absorber needs more condenser water than this guy. This guy needs 3 GPM per ton. In some cases, those numbers are starting to change. These are kind of traditional numbers. And we need 2100. That's going to be the same 2100, I suspect. Look, you say we're going to size this tower for 100 degrees in. We got 94 out here. We got 94 in here. We got 85. So So you see, we're taking this same condenser water flow through the steam condenser first, or I guess through the condenser here first and the steam condenser second, because this is the cold water out of the tower. Pressure drop, feet of water. evaporator, condenser, steam condenser, fluid, water, circuit passes, fouling factor, get you back to your heat transfer days. Let's look at just, oh, hang on, you got a minute. Here we go. Steam flow, 6627 pounds an hour. Supply pressure, 120. That's what it takes to drive that thing. Now, will that save you money versus a centrifugal? Well, you got to go through the numbers. It depends on the demand. It depends on the electric cost. It depends. You know, you can't just look at these things and, yeah, if you've done 100 of them, you can probably look at them. But if you haven't done 100 of them, you've done none of them or one of them or two, probably should go back through the numbers. Okay, I'll quit there. So I'll see you a week from today, quiz on the electrical stuff, and start working on the homework. So I'll get that recording posted to show you how to do more stuff with the carrier program.
On a normal like chiller specification or whatever, what would be the general spec? Like if it said this